All right. Hello, everyone. This is your first lecture in classical mechanics, MA1301. Everything that you need to know about this module is on the on Learning Central. You go to the module under Learning Materials. You can find a data sheet there. Inside that data sheet, you have everything that you need to know about the module. If you have any questions, please do not hesitate to contact me. You can contact me anytime by email. If there's any need at any point to set appointment, we can do that also through email, and then we can have the Zoom meeting. All right, so we're gonna get started with classical mechanics. And one thing I want to say about the structure of the module is that it requires you to do some readings. And I already sent you some readings to do from the study book, which is also on Learning Central. If anyone doesn't have access or doesn't know how to get to the book, please let me know and I will guide you through. The study book is an integral part of the module. For example, for the first thing I asked you to do is to prepare for units. We're not going to cover the units in the lectures. I'm going to start right away with some review of mechanics. Now, some of you might already have had previously some lectures in physics or at school, had some classes in physics. So some of the things that I'm going to start with might be familiar. I'm going to emphasize the application part and the physics. So even though you might think that things are familiar, I do recommend that you come to the lectures and prepare the material that I use. Now, another thing that I wanted to say about in terms of the structure is that you will have tutorials. So this term, we decided to do that we're going to have more tutorials. The lectures are going to be longer than the usual 45 minutes lecture during this period. They're going to be 55 minutes. But normally we have 2 hours today. So the first 55 minutes, or sometimes maybe more, a little bit less, it doesn't matter. And the second part would be a tutorial which is given by the tutor. If you have any questions with regards to the problems that you need to solve, please do not hesitate to contact the tutor. And if you have specific questions that you want the tutor to attempt during the tutorials, please let him know in advance so he can also prepare for the specific questions that you're asking for. All right, so let's get started. I'm going to start with review of kinematics. Now, what is kinematics? We want to be following, going to start from the fundamentals. So if you don't have any background in physics or in mechanics, that's completely fine. And every lecture, we're going to use the previous knowledge and then build on that knowledge and move to the next lecture. Okay, mostly. So we start with kinematics. We're going to start with 1D problem. We have an object, and this object is traveling on. You can think of the object traveling along this line. So it starts at some time, it starts at some point here. Let's call this point x of t1. So at time t1, the object is found here. And it can only move on this line, right? It's a 1D problem. At time t2, it's found, let's say, at some point here. So this will be x t2. At time t3, it's here. This is x of t3. So x is presenting the space, and t is the time. At time t4, it comes back here to this point. So it's traveling forward and backward. I say forward because I put here an arrow. So for me, that would be the increasing value of the space. So this would be forward and this would be backward. You can define it the way you want. We're going to talk about this a lot in the next couple of lectures. So we start here. We go to this point, then this point, we go backwards to point x of t4. And then we go back to original point x of t5, which is x of t4. So this is at time t5. Now I want to make a diagram here of this location x and time. So I said we start at time, and I call this t1, t2, t3, t4, and t5. We have x of t1 and x of t5 and x of t1 is the same, right? Because the endpoint is...
I don't think we can see the board very well.
Sorry?
The camera is a bit far back.
You can't see well?
We can't read the board well now.
You can't read?
The board, we can't read it very well.
Okay. If I write larger, would that help? Let's try. Can you hear me well?
Yes.
Okay. Try to get this closer. Okay, so this is T1, right? This is T2. This is T3. This is T4, and this is T5. This is x of T1. This is, we said it goes first to this point here. So this is x of T2. This point here, x of T3. It goes back here to some point x of T4. Okay, so I wrote here xt1, xt2, xt3, and coming back to xt4. It's traveling along this x-axis. It's the same thing as this one, actually. You can just tilt it, and you get exactly the same thing. And then it comes back to x of T5. So I just put the points here. So we start here, and then it goes to this point here, and then it goes to this point, and then it goes back to this point, and then back to the origin. Remember, it's traveling along the x-axis, and this is just the time axis. Okay, what do we want to find? You want to find the velocities. I have a problem with the how much space we have here. Okay, we want to have the velocities. We want to find the accelerations, and we want to find the speed. So let me write these things here. We want to look at the velocity. We're going to look at the acceleration and the speed. To start with, we look at the average velocity. What would be the average velocity? Well, if I know the location at all these points, at these times, let's take an example. If I look at the average velocity between T1 and T2, So between the two times, t1 and t2, the average velocity would be the distance which has been traveled divided by the time, right? So I can write x of t2 minus x of t1, this is the distance, divided by t2 minus t1. Now I need to be more accurate here. And I'm telling you this now because I want you to pay attention to this, which we will discuss also later on. When we discuss the average velocity, we don't really look at the distance. We look at the coordinate at the location at the final point minus the location at the initial point. That's different than the distance. Why? The distance is always positive. But the location, one minus the other, it depends on how we actually define the increasing value of our axis. If I define the increasing value, for example, as in that direction, so x of t2 is larger than x of t1. In this case, x of t2 minus x of t1 would be positive, right? Which means it would also be the distance in this case. However, I could define this in the opposite direction, and then it would be x of x2, xt2 would be smaller than x of t1. If it's smaller than x of t1, then we will have a negative value here. And this is a main difference between velocity and the speed, which we're going to discuss today. So the velocity between t1 and t2 is the location at x of t2, the location of x of t1 minus the times t2 minus t1. Okay, so far so good. And this, we know in this specific example, is larger than 0. It's larger than 0 because of the way we defined x to be positive, the increasing value of x to be positive in that direction. Or here, it's in that direction. The increasing value of x is in the going upwards. Now, what is the velocity, the average velocity between t1 and t5? Well, that's interesting because we know that at time t5, the object is back to the original location, right? So x of t5 minus x of t1 is 0. So the average velocity is 0. We can also look at a third example between t4, for example, and t2. So between t4 and t2, let's look here. Between t4 and t2, we have x of, so let's write it here. So the average velocity between t4 and t2 is what? Is x of t4 minus x of t2, which is negative, divided by t4 minus t2. Now, t4 minus t2 is always positive, right? So this is smaller than 0. The first thing that we observe is that when we talk about average velocities, we can have a value which is larger than 0, a value which is equal to 0, and a value which is smaller than 0. So the signs here are very important. Whenever you're discussing the velocity, excuse me, or the average velocity, the signs are very important. Now let's look at the following. Assume that now I tell you not only where the object was at these discrete points, but I tell you where the object was at any point, at any time. okay, at any time where the object was in space. So let's assume that the object starts here, goes up, up, and maybe it even goes more up here, and then down here, and then up like that, and then down, and then it went like that. Now you know where the object was at any point in time. If I tell you at this time, you go up here, you tell me it was at this x. If I tell you at this time, you know it's at this point here. And we want also to look at the velocity in a different way. Let's take these 2 points as an example. So x t2 and x t3. We can look at the difference here, which is delta t, and this is delta x, right? So we know that the velocity is delta x over delta t, which is a sign sensitive. So v is delta x over delta t. But we want to look now at something else. We want to look at this. We're going to draw a line between them, a straight line, and look at this angle here, alpha. So the angle here, if you take the tangent of that angle, if you cannot see well, that is delta x over delta t. So now we have an angle there. Now you can imagine that if this point goes up related to the other point, then that angle has to be positive if we define what is positive to be taken from this horizontal line. If this point goes down relative to that point, it would be negative. Okay? So now, just look at the chat. I think there are some. I can only apologize for the quality here. Okay, let's go back to this. All right, so the velocity here is delta x over delta t. And we know that if alpha is larger than 0, then the velocity is larger than 0. If alpha is 0, then you're exactly at the same point. So if alpha is 0, the velocity is 0. And if alpha is smaller than 0, then the velocity is smaller than 0. So this is another way for us to look at the graph, and just by looking at how things are changing in terms of the angle, you can immediately say, aha, the velocity has to be positive, positive, positive. Now the velocity is 0. Let me show you here. Oh, this is too long. The velocity is positive, positive, positive. Here is 0. Now it's negative, negative. Here is 0. Now it's positive, 0, negative, and so on. So this is one way that you can look at the graph and say, aha, I can understand what's going on in terms of the velocity. It's very intuitive. Just to give you another example, if you look between T4 and T5, here, between T4 and T5, you immediately see that alpha is negative because of the way we defined alpha, which is relative to this horizontal. So I should have said clockwise, right? So alpha is positive, alpha, positive, clockwise. Okay. Now, we know that we want to look at the average speed. We looked at the average velocity. We want to look at the average speed. The average speed is the distance. The average speed is the distance divided by the time. Distance is always positive, and time is always positive. So the speed, the average speed, is always, let me put a line here so you know it's the average speed, because we're going to talk very soon about instantaneous speed and instantaneous velocities. So the average speed is the distance over the distance traveled over the time elapsed. Okay. If you just want to take an example, if you travel between between time t1 and t5, let's say that this distance, right, because you're traveling, going up and down and up, and then you have to add all these together. This would be the distance, right? All these curves here, you have to add them together. So the distance now, let's assume that it's 100 meters. And let's assume that it took 10 seconds to go from T1 to T5. The average speed, then you would say, is 10 meters per second. That is the average speed. What is the average velocity? We did it before. The average velocity between T1 and T5 is 0. Why 0? Because at time t5, the object is back at the same location. And it's not the distance, it's the location. It's the location at time t1, at time t5, minus the location at time t1, that is 0. It's the same location. It's not the distance. So here you see an example where the speed, the average speed, is positive, it's always positive, and the average velocity is 0 between the 2 points. Now, let's define the instantaneous velocity. Remember this line that we put between these 2 points. Now imagine that these 2 points, I make them get closer and closer and closer and closer and closer to each other until they almost touch each other. So basically what happens is that, let's say that they almost touch each other at this point here. So the line that I have here is the tangent at that point, right? So now we have the tangent at any point along that curve is what I'm describing here, and what we're going to find that is called the instantaneous velocity. Let's write it here. Instantaneous velocity. So v of t at any time would be, we're going to make it general now. So x at t plus some delta t minus x at t. We can think of this x at t3 and x at t2. But this is now in general, x at t plus some delta t. Delta t is very small, and we're going to do this now. So divide by delta t. And delta t is very small, so we take the limit when delta t goes to 0. This is the definition of instantaneous velocity. Now, you could see from here, maybe, by definition, this will give you dx over dt. So if you know how x is behaving, right? If you know the function of how x is behaving, then you take the derivative of x in time. That gives you the velocity, the instantaneous velocity at that place. And this could be larger than 0, equal to 0, or smaller to 0. And this is exactly like if you want to know now what is the instantaneous velocity, if it's positive or negative or zero, all you need to do is to look at the tangent. Look at that alpha, right? Which we have here. If at this point, because now we talk about the instantaneous velocity, so that at that point it will be the tangent. So at that point, you see alpha is zero. If alpha is zero, the velocity is zero. So you can immediately see, if I want to know what is going on here, the tangent is like this. It goes down, alpha is negative. So if alpha is negative, then the velocity, instantaneous velocity, is negative as well. Now you can have different values. For example, at some v1 maybe here, right? You can have plus 50. At some other point, it doesn't matter where, v6, right? v6, maybe you have minus 150. Now, whether you like it or not, in physics, signs matter. So you would say that the velocity, the instantaneous velocity at that point is smaller than the instantaneous velocity at that point. Why? Because this is positive and this is negative. Even though the magnitude of the velocity at that point here is 3 times larger than the magnitude of the velocity at this point. So you need to be careful about the signs. Okay. In a similar way, we want now to define the instantaneous acceleration. So instantaneous acceleration A at any t. Now I can take, similar to what I had before, I can take v at any t plus delta t minus v at t divided by delta t. And I take the limit when delta t is very small. In the same way, we find that dv dx. So the acceleration, the instantaneous acceleration, is the first derivative of velocity with respect to time. It should be t. Or you can write, you can substitute vt there. It's the second derivative of x with respect to time. You can add t here if you want, just to know that it's at any time. Now these two equations are something that you will have to deal with. You're going to deal with these all along the module. And the same thing, you can see that in the case of acceleration, you can have positive, negative, or zero acceleration. So you can get any of these values. Now, one thing I need to write here, we're going to be using meters seconds. So the velocity, I'm going to write it again here. The velocity is meters per second. And the acceleration is in meters per second squared. Now, let me pause here for a while, even though I said that I would like you to make the readings about the units by yourselves. You're going to have also a tutorial about that today. I want to emphasize one point. The units are very important. If you have a final result, a numerical result, if you deal with a very complicated problem and you end up with a final numerical result, if you don't say what the unit is, there is no meaning of the result, right? It's like I'm telling you the answer is 13. 13 what? Right? So whenever you're solving a problem, you have to make sure that you have the units right. Now, you could say, I know the units of the acceleration. At the end of the day, I can put meter divide by s squared, right? However, you can make use of the fact that the units, when you're dealing with a physical problem, they should match. Meaning that if you have the velocity, if you're dealing with velocities, if you're adding velocities together, the velocity is defined as the, well, let's say the speed, right, is the distance over the time, okay? So you have units of length divided by units of time. So it has to be something like meter per second. It can be also feet per hour, right? That's fine. That's just using different units, and you can convert between the different units. That's completely fine. But it has to be a unit of length divided by a unit of time. Why is this important, and how can you make use of this? If you're solving a problem and you see that you're adding one thing which has some units and they don't match with the other units, you stop immediately and you can be sure that you did something wrong. So this is one way that you can check yourself. It's a very easy way to check yourself. So get used to that. You can find lots of errors in this way. If I'm dealing with acceleration and I find out that I have some variable which is, for example, I have some a plus something like v squared over x. I stop for a second. I know that a has units of length per time squared. If it's easier for you, you can just write meter per second squared. Now I look here. I say, does this make sense? Let's see. This is the velocity. Velocity, I know that it has units of length per time. So it's length divided by time. But it's squared. So it's length squared divided by t squared. And I divide by x, which is length. Now I see that I get length over t squared. Okay, I repeat that. I intended to give some example for something that doesn't really work. So let's see that you get v over x. So v is length divided by time, and x is length. So the units of this is 1 over time, and the units of this is length over time squared. You can't add them together. So you stop immediately, and you know that I did something wrong. I have to go a few steps back and see where I went wrong. It's always good. I cannot emphasize this enough. You do this along the problem that you're dealing with, but definitely at the end, before you're plugging in the numbers, you check the variables. When you add them together, do you get the right units for the problem or the wrong units? And that would give you a hint of where you did, where things went wrong. All right, that was just a comment on the units. Now let's get back to acceleration. Or we can, in a similar way, so I can say the average acceleration, right, is just delta v over delta t. That would be the average acceleration. And it is sign sensitive. How do we know? Delta v is sign sensitive. All right, so I have here a tennis ball. Actually, I have a tennis ball launcher here. Normally, I do these things in a bigger room. Now I have a feeling that something or someone is going to get hurt inside here. All right, so we have a tennis ball here, and I want to launch the tennis ball on the wall. If nothing breaks and it just bounces back to me, I want to calculate the average acceleration. Now, we're gonna start making assumptions. The assumption is that this is gonna be traveling in a constant speed. It hits the wall and then it changes direction. What makes it change direction is that there is an acceleration. We're gonna evaluate this acceleration now. So I have this. Let's see if I can break the screen. All right, ready? All right, wasn't bad. I could also do it I don't know if you can see this here. You can see this here. All right, yeah, I can do it here. So I can drop it down and imagine that, well, this one is a little bit soft, but I have some velocity in that direction, right? Now you can define positive direction the way that you want. You can define it that way or that way. So if I have let's say that the x direction is upwards. So initially we have a velocity which goes down, just velocity, there is no acceleration. All right, so there's a velocity and it bounces and it comes back at exactly the opposite velocity. I might need this. But it's too late. Okay, so we have this. This is my increasing value of x. You can define it the way that you want. You define it the other way, all the signs flip. That's all. As long as you're consistent with what you're doing, that's completely fine. I define it this way. So initially we have v, which is, let's say, plus 5 meters per second is in that direction, so it's minus 5 meters per second. It bounces and it comes back with plus 5 meters per second. What is the acceleration now? Well, to know the acceleration, I have to know the time that it takes this ball touching the floor and bouncing back from the floor, because the acceleration happens only at this time. Okay, so in this case we have say v2 minus v1 divided by delta t. That would be the average acceleration here. So this would give 10 divided by delta t. Now I have to tell you what delta t is. We have to assume some delta t. Let's assume that delta t is 10 to the power minus 2 seconds, which seems reasonable, right? So if we have 10 to the power minus 2 here, you see that we have 10 to the power 3 meters per second squared. Now, if you think about it, in terms of signs, let's double check. We start with a minus sign. We start with in that direction. So it would be minus 5, and it's minus 10. It's just a definition, right? We can define this in the opposite way and it would be plus 10. Okay, so we have an acceleration that has a magnitude of 10 to the power 3 meters per second squared. And this is large. This acceleration is what actually makes things break. I have here glass. The floor is carpet, otherwise I would actually show you how this glass would break completely on a more solid floor. Now it would break, think about in terms of times now. It will no longer have the same time here. it would probably have half of that time because it doesn't rise up, right? So this time, which I just put here, it has some time for the board to decelerate, to come to on hold, and then accelerate back. So if you say that we have half of the time going to complete stop and then half of the time going up until it actually raises up the floor, then you would say that in the case that it does not raise up after you drop it, like this, if I drop this, if I drop eggs on the floor, they will just go down and they will break. They won't go up. And believe it or not, they don't care about the sign. They will break whether you have a plus sign or a minus sign. It doesn't matter. It's the magnitude of the acceleration what matters. Now, the reason that things break because of this amount of acceleration. If you reduce the amount of acceleration, you would be able to have more chances of the objects to survive. This won't break, for example, also because of the material it's made of. I could wrap this with, well, I just noticed something which is terrible. I forgot to press the recording button. Oh no, I did. Okay. But I noticed something terrible anyhow. It's low battery. I need to plug this. Otherwise, we will all go off. Okay, so let's take it to this side. So if now we wrap this this glass with this material, right? What it would do is actually it would increase the amount of time that it is touching the floor to decelerate to zero. Which means, now think about, I'm gonna rewrite it here, but just think about it right now. The acceleration is, what is it? It's delta V, right, divided by delta T. The larger delta T is, so the larger the time it takes it to go down and then go up before it changes direction, the less acceleration you have. And for that reason, if you're biking, for example, it is very important to put something on the head, and the reason that it would actually increase the amount of time of changing the sign in terms of the mass that we've seen here, it would take a longer time. If it takes a longer time, acceleration is smaller. If the acceleration is smaller, the chances of things to break becomes smaller. Okay, so think about this for the next time if you're biking. Let me just clean up this side, and I can carry on. Okay. So if someone falls, an old man or even a toddler, or if they fall on the floor, and if the floor is made of, if you have a carpet, a thick carpet, then as you can feel, right, the hit would not be as bad as if you have a floor which is made of stone, for example. And that is, and also how you're hitting the object, right? If the object has some, let's say that you're jumping and you have shoes and these shoes have some springs, that's very important. That actually reduces the acceleration a lot, which means that your knees, if you like to jump, your knees won't be hurt as much when you're jumping, you're using good shoes. Having good shoes is always important. If you don't do that, you might end up in destroying the joints or breaking your leg due to the acceleration. Okay. in the last 10 minutes, I mentioned now again, for those who weren't here before, we're going to have longer lectures. That's going to be for every week. We're going to have 55 minutes, sometimes even longer. But you're going to have 5 minutes break and then immediately, so you can stay in this room. You don't have to leave this room. You can stay in this room. And, well, you can stay in this Zoom room, right? It's going to be, the tutor is going to actually give it from a different room. But you don't have to log into any other Zoom room. Okay. We defined also the instantaneous acceleration. It's on the other side there. Now let's make some examples. A very easy example. We know x equals 8/6t plus t squared. So we know x at any time. And all we want to know, and this is in meters. So we know the location of the object, which follows this function here. What is the velocity? The velocity is dx dt. So all we need to do is take the derivative. So we have minus 6 plus 2t, and that would be meters in seconds squared in this case. And then we have the acceleration, which is dv dt, which is plus 2t, and that would be meters. Oh, if anyone noticed, thank you. That should be meter per second for the velocities, and for the acceleration, it's meter per second squared. All right. Now, this is a very easy example, but I want to show you that you shouldn't just look at an example. You know how to take the derivative, that's fine. And probably you know also how to build the graph for the example, but I want you to look at the graph in the way that we've looked at the first part of the lecture with alpha and so on. So you would have more insight about the physics that's going on, and not only drawing. You can draw something wrong, but if you know the physics behind it, then you will be able to evaluate properly. Is there any question? Okay. Yes, thank you. Acceleration is just 2, of course. Yeah. To be awake at this time is very tough. Thank you. Acceleration is plus 2. Okay, so we want to let's take this a little bit faster. I'm going to draw here. Can you see this there? Okay. So if I draw, I need to look at the times time t0. I know that x is plus 8 at that time, right? At time t0, x equals 8. So at time t0, it's very easy. I know where immediately x is found. At time, and I know also that v at that time, at time t0 is minus 6. And I know that a is 2. A is constant, so it's at all times is 2. At x equals 0, I can solve this, and then I found 2 times where x equals 0, either at plus 2 or at plus 4. And when the velocity is 0, you can still see, yeah, when the time is plus 3. You can see this immediately here. So now I want to draw these points. I'm in a rush, So I can make mistakes, but this is what we want to evaluate. We understand what's going on here. So this would be 0 for x. This is the x direction, the positive x. This is the x direction. This is the time. And I know that at the velocity is 0 at this point. I know that at time t0, x is here, and then here, and then here. So this has to change direction, and it's negative here. So I think it would be something like this. Now you can say, okay, we're finished with this. That's not the idea here. The idea here is to make use and look and have a little bit more insight by looking at this very simple graph. And the way that I am going to do it, let me just put some numbers. So this is the point 2, and this is the point 4, and this is the point 3, right? This is where the velocity is 0. Let's check ourselves. We know that, think of alpha. The velocity here has to be 0 because the tangent is 0. And this is fine. This is what we see in the figure. And we know that here at the beginning, the velocity has to be negative, right? Because alpha is negative. And here the velocity is positive because alpha is positive. So now I can immediately tell you that give me any time that you want, which is larger than 4. If you take, for example, even at this point 4, right? At this point, I know that alpha is positive. The velocity has to be positive. I can see this from the figure. I don't need to solve anything there. Okay? You can take 5. You can take 3.5. Whatever between 3 and 4, and whatever larger than 4, and you can take also 4. It's all positive. And I can see this because I understand that it depends on alpha. I don't have to solve anything. And now you can check. I say the velocity at time t4 has to be positive. You go here, the velocity at time t equals 4, that's 8, minus 6, that's plus 2, is positive. Okay. The last two things that I want to tell you is that we do have a good intuition for the velocities, but we have less intuition for, that's the first derivative. It's the human nature is that you have good intuition for first derivatives. But for second derivative, it's a little bit more complicated. So for the second derivative, you want to look at you say, okay, what's going on now with the acceleration? Can you see what's happening with the acceleration here by looking at A? Not really. What you need to be looking at is how, by looking at alpha, I mean, how alpha is changing. The change in alpha will determine will give an insight on the acceleration. So it's something which is a little bit more complicated, but we're gonna go over also in the next lectures. The other thing that I wanted to tell you is I want to give you an example for an acceleration, gravity, right? Now I'm standing here, I can jump, I go down because the gravity. Gravity is a restoring force. I didn't want to use this word right now, but you all know what the force is. We're going to define it later on in the module. So we're going to talk about gravitational acceleration. Forget about the forces. So there's a gravity acceleration, right? And because of that acceleration, if I just throw this just like that, then it would initially, I'm just leaving it with zero velocity, right? I'm not giving it any push. I could give it a push, but right now I'm just leaving it. So at this time, at this point, v is 0. And what makes it keeps going down is there's an acceleration in that direction. So it goes down. As it goes down, the velocity increases. The instantaneous velocity increases. Now you have an instantaneous velocity and you have the acceleration. So the further it goes down, the more acceleration it gains, the more velocity it gains, right? The acceleration is the same. So as it goes down, the velocity becomes larger and larger and larger, which means if, and this is something I normally do in the first lecture, unfortunately, I cannot do it in this room, and it's much less nice to do it when you're not actually in the class. I'm going to show you a photo of what I did previously. So if this is true, what I'm saying now, it means that if I just make a black room here and I'm flashing on this while I'm throwing it, then initially it would stand here, and then it would be here, and then the gap would come larger, and then larger, and then larger, and so on. And this is what I hope that you will be able to see here. You need some height also in the classroom to see this. So the way I did this, this is a completely dark room, but because of the strobing, and the strobing is at equal time intervals. Okay, so it's flashing in. We can talk about that later on, but it's very fast. So you see, initially it's at some point here. After one strobe, it's here, and then it's here. Look at the distance. Look how much larger, and then look how much larger, and so on. And then it just touches here before the. All right. So that's all I wanted to show you for this lecture. I will see you next week. I'll just check that Verna is with us. Verna, are you there? Okay. Do you want to take over? I'm going to turn this off from my side. I hope that you all would stay there. But if not, you would have to re-log in, okay? It's the first time we try this way, so let's see what happens. If you do log in, please don't forget to record the session. All right, see you next week.
Okay, hello everybody, can you hear me?
Yes.
Okay, wonderful. I just wanted to know. So now you can take 5 minutes break, and then we will be back with some summary of the lecture today. Feel free to turn your mics on and feel free to ask any question, okay? Maybe some of the rest of your fellows share the questions with you. So don't be shy, please. Mm-hmm. Okay, I'm gonna share my screen, right? So you can see the contents that I'm going through. Yes, it is actually, but we are not going through the whole book. We are just gonna study the chapter of mechanics, right? Do you all have access to this book? Oh, wonderful, wonderful. So the contents that you will see under the section of mechanics is what you will see in this course, okay? Maybe a little bit of waves and acoustics, I'm not sure about that, but we are not going through electromagnetism, any modern physics, because here you can also, neither optics, you can find some quantum mechanics in here, which are really interesting, but they are not the aim of this course, okay? Okay, I believe that the 5 minutes have passed. My name is Berna Gomez, and I'm gonna be the tutor for this course. I will write here my mail. So in case you have any question, feel free to mail me, okay? Anyway, I'd suggest that you raise the questions here in the tutorials because it's very likely that most of your fellows share the same doubts, right? So it would be very beneficial and efficient to share them out loud, okay? As I could see in this first lecture, you went through units and physical quantities and vectors, right? Just a little bit. I think Usama skipped this. It's pretty basic, so I recommend you to go through it. I will have a quick overlook and feel free to ask anything. And he started right from motion along a straight line. Okay, so let's go through this. I believe there is a summary here. So at the end of every chapter, you have a summary with the most important concepts, okay, of every section. So in this case, we go through physical quantities and units, right? You all know that length is measured in meters in the international system, please. I think we are gonna work in the international system mostly, right? So I recommend you to stick to meters and kilograms, please. It's gonna be easier for everybody. You all know what how work is measured. Can anyone write in the chat or speak? What do you understand for work? And I think yes. I think that the book covers pretty much everything that you're gonna see, but I cannot confirm that it covers 100% what you're gonna see, but a big part of it. Okay, work is measured in joules. Okay, joules. It's important, this concept. Okay, and a joule is defined as the work done by a force of 1 Newton acting over a distance of 1 meter, okay? So joule is related to force and distance. That's important to know. If we understand the units of the physical properties that we are measuring, we will understand how to calculate them, right? If you know that work is measured in joules and you know that the joule is related to newtons and meters, you can understand that you need force and distance to calculate work, okay? So that's why it's very interesting that you go through this whole unit. You have a read, it's a very nice read, okay? So just go through it. And also what is a Newton, right? It's important to understand what is a Newton. That Newton is related to acceleration okay? And it's also related to mass, okay? So basically, is the force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second squared, of course, okay? So we have acceleration if we have force, and if we have force, we have acceleration. We will understand that deeper in later chapters, especially in the, let me see, in Newton's laws of motion, okay? Where you will see that anytime that we have a force, we have an acceleration, or most of the times that we have a resulting force, okay? What else do we have here? Significant figures. Well, this is related to accuracy and uncertainties, right? For example, if we are using here 5 significant digits, and here we are using 2, we cannot go beyond those 2, right? So we are always limited by the amount of digits that we can express, okay? I recommend you to stick to 2-3 significant figures. Don't go beyond that. I don't think you need to go as precise as farther than millimeters, for example, in meters, right? So I hope you all are familiar with this and understand it. Well, it's also important to understand the difference between scalars and vectors, right? For example, how would you measure temperature? You would measure it with degrees, right? Which is a scalar quantity. But once you go to vectorial quantities, they also express not only a magnitude, but also a direction, right? For example, let's say acceleration, let's say velocity, right? So they are related to a direction, okay? It's important, the sense where are you moving to, right? So it's not the same to have a positive, negative, right? Additions. So I also recommend you to get familiar with all type of operations with vectors, okay? So addition of vectors, how do you add 2 vectors? How vectors are composed. So I believe you are all familiar with this, right? Do you have any question, guys? Okay. So okay, thank you guys for the answers. I thought I was talking alone. Wonderful. Okay. So you are not familiar with this type of things. Okay, so I'll get to the, okay. Vectors and vector addition, okay? So there you can go to the section, right? Okay, vector addition. Well, how to calculate the magnitude of a vector? So you would use the Pythagorean theorem, right? Addition and subtraction. Okay, so I have a problem, is that I don't have a blackboard here. So for the next tutorials, I'm gonna have access to a blackboard and I will be able to write everything. It's gonna be much easier and much more understandable, everything, okay? I'm sorry if my resources are very limited now. Okay, let me see if there is any good example here. So components of vectors, this is where I wanted to get. Okay, so for example, in this vector that we see here, A, is a 2-dimensional vector. Why do we know it's a 2-dimensional vector? Because it just has 2 components, okay? So it can be described just with two components, X and Y in this case. If we work in 3 dimensions, we will have an additional component, which will be Z, let's call it Z, okay? What happens when we add, or I think yes, it's very likely that you will do 3D vectors in this module. Yes. So get familiar with 2-dimensional and 3-dimensional vectors, okay? Subtractions, okay. So if I subtract or add two vectors, what I would have to do is to work, for example, with the components of x and then with the components of y. I wouldn't add or subtract the component of by to ax, okay? If I'm working with the x component, I would go for the bx component, okay? That's really important that we are consistent, okay? Well, also the angles that the vectors describe between themselves is important angles, because we won't be able to compute scalar or cross products if we don't have the angles. So we have to understand the Pythagorean theorem, right, to calculate angles. So we always can imagine this triangle, and we know all the relations, right, to cosines, sines, and sides, okay? If you have problems with this, I can try to explain them in the next tutorial, because I will have a Blackboard and it will be way easier. Here is really hard to explain all these concepts. They are very visual concepts that you have to work, okay? So also, I want you to understand that mathematics at the end of the day is like any sport. You have to work it out every day and keep yourself sharp, okay? So the more you work on those exercises, the better and the deeper your understanding is gonna be on them. Oh, sorry, I completely misunderstood them. I completely misunderstood them. Sorry. Okay, so you don't have questions about it. Sorry. Okay, that's great. That's great. Okay. Thanks for the clarification. Okay, so once we know how to add and subtract vectors, which is very important, we also have to know scalar products and vector products, okay? It's important that you keep in mind the notation, okay? The scalar product or the dot product is expressed with this dot, okay? And you have also to understand that the order in this one is not important, but in the vector product is important, okay? So this type of properties, I believe you will see them in other subjects, but it's good that you also practice them for this subject because you will see it a lot. And vectorial products, okay? Just not much more to say than what it says here in the book. I don't know if you have any problem with this, guys. If you understand, this is very important, the right hand rule for vector products, which is expressed here. So basically what is happening here is that the result of this operation is another vector that is perpendicular, is orthogonal to the plane that is described by A and B, okay? But the question is in what direction, upwards or downwards? Well, the easiest way to know this is just to take your right hand and basically to emulate A closing towards B. So then the direction of your thumb is gonna be the direction of the resultant vector. I don't know if am I clear in this? Do you all know the? Okay, the right hand rule. Okay, so well, I'm not. I don't write the exam, so I don't know what Usama would write. But this is important to understand torques. Okay, so I wouldn't ask you to compute a vector product, but I might ask you to compute the torque, okay? The torque and angular accelerations, angular velocities are gonna be studied further on this course, are very important, and you really need to know what is a vector product to compute torque, okay? For example, when you remove the cap of a bottle, you can see that the cap goes in one direction, okay? And that's the same as the right hand rule, okay? So you can also think about that. So it's very important. So because vector product, the order matters. So if we are computing B cross product with A, the direction would be completely different. You have to understand that. So please understand what is a vector product, understand the right hand rule, please. It's very important because if in the exam you write the direction of the resultant vector wrong, it's very likely that Usama will put a fail on that question, will mark you wrong, okay? Can you be more clear? What don't you understand, please? the right hand rule or vector products? Okay, the right hand rule. It's very hard to explain it if I don't have a blackboard or anything. Okay, so basically you understand that it matters the order, okay? It's not the same A multiplying B than B multiplying A. And I will tell you why. Because of the right hand rule. And how does this work? Okay, if we are computing A multiplying B, we just put our hand in the way that our fingers close in the same direction that A would close towards B. Okay, like you can see in this figure, the fingers are closing in the direction of this angle. Do you see this small arrow? So once you do that, you will realize that your thumb is pointing in a direction, and that's the right direction of the resulting vector. I don't think I can explain this more clear without a blackboard. Maybe you can try to find some videos in YouTube about the right hand rule. It's really important, vector products, okay? They are really, really important for this subject. And scalar products are also really important, okay? So please try to understand everything here. Then you have some exercises, okay? So all these exercises, I encourage you to suggest exercises. So if you mail me with any exercise, I will solve them in the next tutorial for you guys, for everybody, okay? So everybody understands the exercise, okay? I will also mail you all with 5 exercises that I strongly encourage you to solve by yourselves. And I will provide you the solutions in the next tutorial, okay? So the 5 exercises will be chosen from all these exercises at the end of the chapter, okay? So, for example, this exercise 1.11, okay? So let's think about it. A group of scientists, blah, 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 determined that the critical mass of this element is about 60 kilograms, okay? We know the density, so we know mass. We know density, which is expressed in grams per centimeter to the power of 3/3, okay? What would be the radius of a sphere of this material that has a critical mass, okay? So first of all, we have to be consistent in the units, okay? We cannot work with kilograms and grams at the same time. So we would have to convert one of those units to compute them, okay? How would I solve this? Well, I can know the volume of 60 kilograms of this material if I know the density, right? Is that clear? Do we all know how to calculate volume with mass and density? Okay, wonderful, brilliant people. So this is full of smart people. I like that. What's happening here? I will minimize this, okay? Okay, wonderful. And we all know how to compute the volume of a sphere, right? Easy. You can just Google it, right? It's super easy. We can compute the volume of a sphere if we have the radius. So we just have to equalize the volume that we can compute of this material to the volume of a sphere, and then we can just infer the radius. Okay, so I want you, this is one of the 5 exercises that I will ask you to do, please. Just to know that you know how to be consistent in units. Here you're working with different. Also, orders of magnitude is really important, right? As I saw, someone was talking about a tennis ball, right? And if I'm calculating the mass of a tennis ball, I wouldn't expect it to be 1,000 kilograms, right? I would expect it to be in the order of, let's say, less than a kilogram, or 0.5 kilograms, for example. So then you can see if your problem is right or wrong. So since we're working in physics, I don't know if the exercise solutions are in the book. I don't know. It's likely that they are not. It's likely that they are not. So there are some answers, right? But we don't have every single answer. No, you don't have all the answers. And even though if you have the answers, the number is not as important as the way you are solving the problem. So you are also going to be evaluated on the way you solve the problems, okay? The way that you engineer it. That's really important in physics. I don't know why it's just the odd number. I don't know. I don't know. I haven't written this book. No, we are gonna teach you the same chapters, but I've been told to start by this one. So I just do what Usama suggests me to teach you, okay? So I'm not gonna teach anything. I'm just a tutor. I'm nothing. So I believe all these type of questions should go to Usama. Just ask me questions about the problems, something that you don't understand. I'm here just to support you guys. So let's make this informal. Let's create some debates. Feel free to talk, to say anything in these tutorials. Please feel free to email me with any question, okay? I just want to make sure that you understand the topic. That's why for the next tutorials, I will have a blackboard, and I believe they will be more understandable, okay? No, you're not supposed to look much at uncertainty, but you're supposed to understand it, since it's a very basic and important concept in physics and also in mathematics, okay? So definitely look at it, but I don't think you will receive a question about uncertainty in the exam. I don't know, maybe. Well, this time you will have to put a little bit more effort on that. But in this book is really understandable. Okay, so basically here uncertainty is gonna be related to 2 sources. Okay, one of the sources is gonna be our device to measure things. Okay, for example, if I have a scale to measure weight, and my scale only goes to decigrams, I have an uncertainty associated that is gonna be related to centigrams. Okay, I cannot measure beyond decigrams, so I have an uncertainty. So if the scale says I weigh, let's say, 70.1 kilograms, I don't know if it's 70.15 or 70.05, right? So this is the uncertainty I have. So this is one of the sources of uncertainty I have. The other source of uncertainty I have is that I'm limited by the number of digits that I can express in the paper or in the computer, okay? So those are the major sources of uncertainty that you will find in this subject, okay? So also be consistent. If you're working with 4 significant digits, as you can see, 70.15, try to work everything with 2 decimals, okay? So if you're working with 2 decimals, work always with 2 decimals Don't express some quantities with 3, some quantities with 1, some quantities with 2, because that's inconsistent, okay? That's important as well. So try to be consistent with your numbers, with the units, because you can do a brilliant exam, but if you're not consistent with units and with digits, your mark can be severely affected. So you just pay attention on it. I believe you're smart people and you will understand this. What else do we have? Okay, today you have gone through some basic kinematics, right? Displacement, time, average velocity. Okay, so, well, I wanted to also encourage you to do another exercise from here. I would like you to do the exercise 1.95. This is a really interesting exercise, okay? So I will give just a brief intuition on it, and then I would like you to work it at home and come with any question that you have about it. So you're given two vectors, right? A and B. So because of the components of those two vectors, you can tell they are two-dimensional, right? We are working in 2 dimensions. Why do we know this? Because I stands for the x-axis and J stands for the y-axis. This is a consensus in the scientific community, okay? So you normally see I associated to x-axis and J associated to y-axis, okay? Two-dimensional. We are also told that the third vector C lies on the xy plane. What else do we know? Vector C is perpendicular to vector A. So they describe 90 degrees, okay? 90 degrees. This is really interesting. If then you go to this summary and you see that scalar products and vector products are computed with the angles, okay? So that they describe 90 degrees is gonna make your life much easier, much easier. The sine of 90 degrees, 1. Cosine of 90 degrees, 0. Okay, so keep that in mind. What else do we know from here? Okay, we also know the value of the scalar product of them. And with all this information, we have to find the components of the vector C. So more important than the solution, I would like to know how would you solve this exercise, okay? So please spend some time during this week and try to solve it. Provide me some good answers by next tutorial, please, guys, and I will give you the solution. What other exercises can be interesting? Well, most of those exercises are related to vectors, okay? So if you mail me with some of them before Friday, I will solve them on next tutorial. Otherwise, by Friday, I will mail you with 5 exercises that I want you to solve, okay? So feel free to suggest exercises. Okay, wonderful. So now we are moving towards some kinematics, displacement, time, and average velocity. So are you all familiar with derivatives, first derivatives and second derivatives? So does everybody know how to compute them? Okay, that's wonderful because this is related to derivatives. In what way? Okay, when we compute instantaneous velocity or instantaneous acceleration, we have to compute derivatives, as you saw in the lecture, okay? So displacement, okay, final position, and we subtract the initial position, okay? Displacement. So those are very standard notations. So be familiar with this type of notations that you will see all along the course, okay? For displacement, delta x, important. So we are working on a straight line, okay? That's why we just have one-dimensional displacement, okay? If we had two-dimensional displacements, we would have to add another component, which would be y, okay? So try to go through this exercise. Average velocity, well, that would be the total displacement divided by the total time that we took to cover this displacement. But this is the average velocity, as Susama pointed out very well. The instant velocity might not be constant, right? So if we don't have constant velocity, we might be interested to know what is the velocity at different points. How do we understand this? Well, we have to go to continuous calculus, okay? To the calculus of the continuum. How do we understand continuum physics? Well, we understand them through the integral calculus, okay? Integral calculus is related to integrals and derivatives. Derivatives are really important. If we take an infinitesimal distance, a distance that is infinitely small, we would go to the differential of x, right? And the differential of x divided by the differential of t is the derivative of x in time, okay? So what is velocity? Velocity is the derivative of the position in time. That's really important to understand, okay? Instantaneous velocity, what I just explained, the derivative of x with respect to the time, okay? Which is just taking the limit when the delta t goes to infinitely small, tends to 0, okay? Just have a read on this book. This book is gonna guide you very well through the course. And if you understand this section, mechanics, I believe you will be really good to obtain a good mark in this module, okay? So don't postpone it. Start from today or from whenever you have time reading it. Just have a quick read before you go to sleep, anytime. Okay, so now we understand average velocity, instantaneous velocity. Well, finding velocities in the chart. Average and instantaneous acceleration. So what is the acceleration? Well, the acceleration is the change of velocity with respect to the time, right? So this would be the average. Every time we have deltas, we are talking about average, okay? Like capital delta, sorry. Where is this book? Well, I obtained it from the Learning Central. Do you have access to Learning Central? Can you see the book in Learning Central? It should be on Learning Central. However, please take a moment to take the name of the book, please, the edition, everything, note this or make a capture. So then maybe you can obtain it from the library or from any other source, okay? Okay, thanks, Michael. Wonderful. Thank you very much for the help. Okay. Yes, it is there, actually. Thank you, James. So everybody can get the book from there. This book is going to be really helpful for you guys. I would say this book is essential for you in this course, okay? If you go through this, you don't have to go through the whole book. You just have to go through the section mechanics. So we are in classical mechanics, okay? So don't go to, well, motion in 2 or 3 dimensions is, sorry, don't go to waves and acoustics yet, okay? So just make yourself familiar with classical mechanics. So far we're going, I recommend you to go through the first units, physical quantities and vectors. Just read it, understand it, get familiar with it. You don't have to work it very hard. Just it's more important that you understand it. Watch some videos in YouTube, find other resources, other materials. Internet is full of them. feel free to ask me. I provided you my mail, okay? So you have all the resources at your hand, okay? I'll continue with acceleration, okay? So as we said, the acceleration is the change of velocity with respect to the time, okay? But what happens if we go to instantaneous acceleration? Let me see what happens if we go to instantaneous acceleration. Well, as we can see here, the acceleration is the second derivative of position with respect to time. And what does this mean? This means that acceleration is also the first derivative of velocity with respect to time, okay? So for example, we have here a chart, right? In this chart, the green line is the velocity. It's a plot of the velocity with respect to the time. How could we infer the acceleration from this chart? Well, we know that the derivative is defined as the tangent line on a point, right? The tangent line to a function or to a curve on a point, right? And is the slope, sorry. So if we have the chart of the velocity, we can always infer the acceleration by calculating the slope of the tangent line, okay? Otherwise, if we have the expression that describes this motion, we can always calculate it by differentiation, okay? Because we know that the first derivative of the velocity with respect to the time is acceleration. The second derivative of the position x with respect to the time is also acceleration. So it can be calculated by two ways, okay? We are talking, of course, about instant acceleration. We talk about derivatives, we talk about instant acceleration. We talk about increments, capital delta, this delta. We talk about average, okay? This is a very important concept, okay? So keep it in mind, please. So basically for the next week, we are coming to the end. I'm told that I should be finished by 45, by 2:45. So in these 2 last minutes, I will give you a few problems. And in the final 5 minutes, I would like you to try to suggest some exercises, ask any question, please create some debate forum. It would be really interesting. Okay, so for the next week, I would like you to go through the first unit, through the first chapter, which is units physical quantities and vectors, please. Okay, read it carefully. And so far, solve the questions 1.95 and 1.75. I will provide you 3 more questions to solve unless you recommend or suggest some of them, okay? So start by that. Also have a read to the second chapter. Just get familiar with it. Next week, I will mail you with some questions. So the way we are gonna work is that before the tutorials, I will mail you with some questions. You aim to solve them at home. And then in the tutorial, I provide the solutions. That's how we are gonna work through the course, okay? And normally I will provide around 5 questions, sometimes less, sometimes more, depending on the weight of every question, okay? I will choose them myself. So it doesn't mean that Usama is gonna choose them for the exam. Keep that in mind also, okay? But I will try to choose the most representative of every unit, okay? So far you can start by reading the whole chapter, the first 2 chapters, just read them, get familiar with them, solve the questions that I mailed you, and ask me any question that you want, please. So don't be shy. So now for the last 5 minutes, do you have any question? Just spend 4 minutes reading the questions and suggest anything that you would like to see solved by me in the next tutorial, please. Okay, any recommendation, any suggestion, please, guys? Okay, wonderful. 1.56. Let me have a look to it. Oh, sounds interesting. Okay, so let's do that question. Question 1.56. Okay, aim to do it at home, guys, and I will solve it on the next tutorial, okay? If you have any suggestion, feel free to mail me or anything, any question, whatever you need, okay? 1.72, let me have a look. Dislocate the shoulder. Okay, wonderful. 1.73, 72, sorry. Okay, so far we have 4 questions. Okay, wonderful. So let's leave it here, guys. You have some work to do by next week. Aim to do it. Otherwise, I will provide the solutions. Also, any question that you can have, raise it on the next tutorial, or feel free to mail me. Okay. Have a nice week, everybody, and good luck with exercises. You're all welcome.